put it together, which is ridiculously hard. The positive nucleus of one hydrogen and the positive nucleus of another by no means want to get together and make one more big nucleus. This really simple drawing is exactly what's happening here. You're taking two individual positive nuclei, forcing them together to make one bigger nucleus. That's really, really hard to do. The force that holds the nucleus together for all atoms in the world is called the strong force. It's really strong. All right? That makes sense, okay? If it wasn't, people would just disintegrate, okay? We'd probably never even be formed. But the nucleus is really strong, and it doesn't want to be near another one because positives will repel, right? So that's a very difficult process, requires a lot of heat and pressure. Well, where is there a lot of heat and pressure? The core of the sun. Insane amount of heat and pressure, right? So that's why the sun and stars, all stars do fusion, nuclear fusion, and that's what they do. But to do this on Earth is very difficult. We can do incomplete, in other words, we can't completely fuse atoms into one nucleus. And I admit I don't know a whole lot about the details of this, but I do know we can't really successfully completely do this. It's just it requires too much energy, and there's too many forces involved that don't want to do that. So it takes a lot of energy. It's very, very hot. All right. So what I want you to write in your notes: this is more powerful than fission. Okay, I'm not going to write it. You can write that. More powerful than fission. It produces more energy. We should do that over here, big E. More energy than fission. So fission creates that nuclear chain reaction. Fusion doesn't. Okay? Fusion, once that helium is created, then that one fusion reaction is done. Then more hydrogen can fuse, but it isn't a chain reaction. It's different. All right, so this is really, really powerful, but it's also really, really hot. And it's very hard to control because, again, all the forces involved that they don't want to be put together. And just to review, again, because Sean wasn't here. All right, if this is our uranium, you don't have to draw this, just watch. And here's our neutron. When we hit that uranium and it splits, here's our two pieces of fission. And remember, now 3 more neutrons will go off, and they will hit more uranium. All right, and then that'll split, and that'll split, and that'll split. And then it goes on and on and on until we run out of uranium. So here's your uranium. Here's more uranium, more and more, and then these are your byproducts. So this is what fission looks like. Fusion is a lot more simple. You just take 2 nuclei, put them together to make one. You would think it would be easier, but it's much harder to do. Much harder. Because if you slam this with a neutron, it's willing to, it wants to break apart essentially because it's really unstable. Whereas hydrogen is stable. It doesn't want to come together and make helium. So just trying to compare the two, okay? Fission versus fusion. It's important to know the difference. Both produce lots of energy. But fusion produces more, which makes sense, right? Is the sun hotter than a nuclear power plant? Yeah. Okay, nuclear power plant, if it was the same amount of energy and heat as the sun, it would melt the earth, right? So that wouldn't work out too well. So let me show Sean that video, and you guys can watch it again for fun. And then we will talk about pros and cons of nuclear power and learn about half-life. All right, lights please, ready. Had a good no, that's not a picture of yesterday of fusion I want to show you. Should have saved it. Is that? Maybe that's it. Nope, the connection was not private. These new filters are super great. just eat till that thing. There's fusion. Now, if I can zoom in a little bit here. Okay? So tritium is H3 over 1. Deuterium is H2 over 1. So 1 would be the proton here, the positive, and the blue one is the neutron. So there's your mass of 3. 1, 2, 3. Mass of 2. 2 over 1, 3 over 1. When they fuse, you get a neutron that gets kicked out. So the neutron is a byproduct, but here's your one nucleus. So fusion is when you take two small nuclei and put it together to make one larger or one more massive, meaning it has a larger mass. It has 1, 2, 3, 4. So, I'm sorry, that's the intermediate. Here's your product. Here's your 4 over 2 He. So 1, 2, 3, 4. So you have 4 particles in the nucleus. This has 3, this has 2, and again, it loses a neutron. So that's just an example of seeing fusion instead of me just writing it down. All right. Oops. Those are half-life graphs. All right, here we go.
Nucleus to form 2 new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into 2 lighter elements, such as krypton-91 and barium-142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amounts of energy in the form of heat, light, and ionizing radiation.
So that's your chain reaction. It just kept exploding. As long as there's uranium for the neutrons to hit, then it will continue to react. Okay. Now half-life is what I want to talk about now. These are 2 great examples of what you're going to get in lab. When you're done counting the heads of pennies, you're going to graph it, and it's going to look just like this. Okay? It's a downward slope, which makes sense. Take this one, for example. Here's like all the pennies, right? And then when you dump them out, about half of them are heads. Then you dump them out, about half of those are heads. And about half of those, and about, so your graph in lab will look just like this. So the point of lab is to help kind of conceptualize what the heck is half-life. Every time an element goes through one half-life, half of its mass has been converted to a different element. And that's what this shows. So if you start with 10 grams of a cobalt-60 isotope, 5 grams of it has transmutated into something else. And then 5 grams of CO remains. And then another half-life passes. Half of 5 is 2.5. So 2.5 have transmutated, and 2.5 stays cobalt-60. And the cool thing with half-life is every single atom, it's kind of a coin flip. And I know that Mr. Decker uses the same terminology. So we don't know which one's going to transmutate or which is going to stay. So it's like a probability with each one, but we do know after a half-life, half of them will have transmutated, half will not. So I just wanted you to see that since I got it pulled up. Let's take a little bit of notes here, and then we'll be done for the day. Okay, lights please. All right, so radioactive half-life. Table N has the half-life for a lot of these elements on there, so that's useful. Radioactive half-life. All right, so let's define it. The time it takes for a radioactive isotope to lose half of its mass, and I'm going to put lose in quotes, lose half of its mass. And then another thing I want to add to that is the half of the mass is transmutated into a new element. And hopefully that new element is more stable. So that's really what half-life is. It's the time it takes for half of an isotope to lose its mass. Or, I said that backwards. It's the time it takes for an isotope to lose half of its mass. And that starting mass, let's say, is irrelevant. You could have 1,000,000 pounds of something, or 1 pound. The half-life is the same. So on table N, and we're going to write this right now, on table N, these numbers are, where am I? Right here, are constant. So for gold 198, if I have a sample of gold 198 this big, or I have 1 atom of it, the half-life is still 2.695 days. These are constant. So right underneath here, half-life never changes. Half-life never changes. It doesn't matter if the sample's hot or cold, in a vacuum chamber or whatever. It doesn't matter. The half-life is what it is. It's nothing we can affect. Okay? So again, you have 10 grams of it, 1 gram, it doesn't matter. It is what it is on table N. You can look these things up online. Alright? Kind of like measurements, right? Like a meter stick. A meter stick's a meter stick. Something, if this desk is a meter long or you have a piece of paper a meter long, they're still a meter long. Doesn't matter what it is. Same concept. It never changes. Doesn't matter how much you have. Okay, now, Mr. Decker's lab didn't see this, but my lab did. But I'm going to do it again. Let me use magnets. And I want you to, do you guys happen to have maybe 2 colors? Like a pen, pencil, blue, black? If you want to grab a marker, you can do that. So I want you to draw at least just 2 different pictures. Okay. So I want you to draw, let's use, I'll do what I did in the lab. We're going to have 16 of these here. So we're going to have 4 rows of 4. So in your notes, just draw 4. Actually, wait. I'm not being very smart here. You don't need 2 colors. What can you do? Yeah, just color it in. That would be a lot easier. At least I came up with it before somebody called me out. So yeah, just make 4 rows of 4 open circles. Don't shade them in. All right, and we're gonna pick an isotope from table N. I don't care which one. Kara, pick one. What's your favorite isotope on table N? K37. Great choice. All right. So let's see. How do I want to do this? I want to make sure we have some room to the side here. We'll do this. All right. K37, 19. What type of decay does it undergo? Anybody? What does it release? What does it emit from the nucleus? Positron. 0 plus 1 E. And then it transmutates into argon. Okay. Now, somewhere near your picture, you need to set up a chart.
We don't have that much room.
Well, figure it out. Sorry. Mass K. This is argon. Time. Half-life. It's important to write it down, but it's really more important just to watch up here and see what's going on. Because this, we're gonna run out of time. You're not gonna be able to do any of your homework, basically. I was a little too ambitious. Okay, that sheet that says half-life number 1, number 2, you can't do any of that. This sheet, the back of the nuclear power plant, you can do 4 of them. Better than nothing, I suppose. So on this one, you can do 66, 67, 68, and 70. You can't do 69. So do those. So just skip 69. All right, just because we don't have enough time. But I'm going to continue here, so stay with me. All right, so just do that for tomorrow. I didn't give you the decay. So number 70 says complete the equation. Just write it from scratch. So when it says decay equation, that's like this on the back of the homework that was due today. It's the exact same thing. All right. Okay. So, all right. the half-life, so back to this now. The half-life of K37 is 1.23 seconds. So, make sure everybody's with me. This is potassium 37, and we have 16 atoms. So each red circle is an atom of K37. So if each one, it's a little confusing, but let's say each one is 1 gram. That's impossible, an atom doesn't weigh a gram. But just for the simplicity, let's say these are atoms of K, and they also have a mass of 1. So initially, we have 16 grams of K37. Now, it's really important. This chart is how I teach half-life. This is how you're going to be showing work on homework, tests, quizzes, labs. You're always going to set up this chart. Mass, time, half-life. This AR is kind of just for this example. All right, so we start with 16 grams of K. So we act as if nothing has happened. It's like we could stop time. Okay? Nothing has happened yet. Now we hit our stopwatch. 1 half-life passes. Well, how much time has passed? 1.23 seconds. So 1.23 seconds. So after 1 half-life, how much potassium, according to the definition of half-life, should we have left? 8 grams. Very good. Now I use, and you guys can shade it in, and this might be hard to actually take notes on, I understand that, unless you redraw it. But randomly, 8 of these will turn into argon. So argon is going to be yellow, and potassium is going to be red. So 1, 2, 3, 4, 5, 6, 7, and this one, 8. Half of them have now decayed.
Wait.
So we started with 16.
You only have 12 up there, by the way.
Oh crap! I knew that looked weird.
Yeah, I was like, okay.
Sorry, guys. Let's do that. Does that make more sense?
Yeah.
Sorry, guys. I kept saying 16 and I wasn't counting. I was just going off of what I did yesterday. Sorry. So we started with 16. That makes more sense. So now we have 1, 2, 3, 4, 5, 6, 7, 8. 8 of these red potassium have transmutated into our yellow argon. So this side here is to show argon went from 0 to 1, 2, 3, 4, 5, 6, 7, 8. Obviously, I'm out of time. I'll pick up with that tomorrow. It's important we go slow instead of rushing the homework. So